Welcome back to the Explainer. Today, we're basically stepping into the boots of a shift charge engineer. We're going to completely decode the massive array of automated defense mechanisms packed inside the GE9FA gas turbine. We're breaking down exactly how this incredible machine protects itself, all the way from the exact moment a start command is issued, right through to steady-state operation on the grid. So picture this. What exactly goes down when a massive gas turbine, spinning at a totally mind-boggling 3,000 RPM, suddenly detects a critical fault? Well, to figure out how this billion-dollar piece of hardware actually protects itself, we really need to look at its automated reflexes. Think of it like a giant industrial immune system. It's a highly complex logic network designed to instantly neutralize threats before they can result in catastrophic failure. Now, before we even think about initiating that startup sequence, we absolutely have to clear up the difference between a trip and a shutdown. A trip? That's slamming on the emergency brake, literally right this second. It's a sudden, immediate isolation of the system to save the hardware. But a shutdown? That's way more of a controlled, methodical deceleration. Think of a fired shutdown, where the machine reduces its load systematically. All right, here is our roadmap for today. We're going to break down these protections chronologically. First up, pre-ignition protections, then post-ignition protections, followed by protective status 1 and 2, then protective status 3 and 4, and we'll wrap the whole thing up with automatic and fired shutdowns. Let's get into it. Section 1. Pre-ignition protections. Defenses before the fire. Think of this phase as a ridiculously strict security checkpoint that the turbine absolutely has to clear before even a single spark is lit. Before that ignition even happens, the controller is playing the role of an uncompromising bouncer. It is aggressively scanning the system. We're talking checking for auxiliary servo faults, gas leak test failures, and any undervoltage on those super critical lube oil pumps. It's even sniffing out hazardous gas levels in the turbine compartment. An alarm will sound if gas hits 7%, but if it spikes to a high of 17%, boom, the unit trips immediately. If literally any single parameter fails here, even if it just fails to ignite after the warm-up timer, the entire sequence just stops dead in its tracks. Moving on to Section 2, post-ignition protections, managing the flame. So once that warm-up timer finishes up and the flame is actually locked in, we enter the post-ignition phase. And suddenly, thermal parameters become the biggest threat on the board. The very second we have fire, the protective logic totally shifts gears. Now, the system is watching that flame like a hawk. If all 4 of the flame detectors fail while it's running, immediate trip, no questions asked. The controller is also on high alert for some serious lube oil overheating. Specifically, if the header pushes past 79 degrees Celsius, that's a huge red flag. Same goes for compressor bleed valve trouble. If those valves fail to close during pre-start, or if they don't open properly, the machine trips right then and there to save the compressor from stalling out. Now, one of the absolute most complex defenses in this post-ignition phase is the exhaust temp spread logic. It's basically a math problem. The system calculates the temperature difference, or the spread, between various thermocouple readings to sniff out localized combustion trouble. Because if it doesn't catch it, that localized heat could literally warp the hardware. So here's the deal. If spread 1 or 2 hit a high state, especially with adjacent thermocouples, the machine automatically steps down to spinning reserve. But if those spread 3 and 4 alarms persist, or if multiple adjacent sensors fail completely, it skips the warnings and just trips the whole unit entirely. And speaking of exhaust temperatures, let's talk about the magic number, 1250 degrees Fahrenheit. That's about 676 degrees Celsius. If the average absolute exhaust temp ever pushes past that critical threshold, the machine triggers an exhaust over temp trip. Instantly. There is absolutely no waiting around here, guys. The thermal stress at that heat level is just way too extreme. Section 3. Protective status 1 and 2, the running defenses. So as this massive turbine accelerates up to its 3,000 RPM synchronization speed and finally hooks into the grid, it activates protective status 1 and 2. These are essentially your core steady-state defenses. Protective status 1 is your ultimate physical failsafe. It is constantly, endlessly scanning for active fire indications across every single zone, while also watching out for generator trip lockouts coming from the electrical relays. And it enforces some incredibly strict mechanical limits. For example, if the bearing lube oil return pressure drops to just 0.7 bar, or if the exhaust pressure spikes up to 24 inches of water, yep, the turbine trips to save itself from literally tearing itself apart. All right, let's look at protective status 2, which really builds on those mechanical safeties. Status 2 watches the fluid and mechanical pacing with just incredible precision. It's constantly analyzing P2 gas pressures and verifying that the stop and speed ratio valve positions exactly match their commanded references. I mean, even a tiny position error of just plus or minus 5% will force a trip. It also keeps a close eye out for any loss of ventilation in the turbine compartment, because as you can imagine, that could lead to some highly dangerous gas accumulation. A real standout feature in Status 2 is the vibration trip logic. The GE9FA actually uses dual controllers for this. You've got the normal G12 controller, and then you have the G12S Safety Instrumented Level, or SIL controller. This SIL controller uses a rock-solid 3 out of 4 voting logic. What that means is, if 3 out of the 4 seismic sensors detect vibrations hitting exactly 25 millimeters per second, it bypasses all the other logic and instantly trips the unit. It's an incredibly rigid, reliable safety net, purposely designed to catch catastrophic mechanical imbalances the absolute millisecond they happen. Moving on to Section 4, Protective Statuses 3 and 4, Control Signaling and Manual Overrides. Our final protective statuses shift the focus just a bit, looking more at the integrity of the digital control signals themselves, plus any human interventions. So, what actually happens if the brain of the turbine loses its precise control? Well, if the gas control valves, that's G1 through G4, fail to track their references for just 5 seconds, or say they start oscillating by plus or minus 3% for 25 seconds, status 3 and 4 are going to step right in and cut the cord. On top of that, if the control speed signal deviates by 5% from the calculated speed, these statuses override everything and initiate a trip. Oh, and by the way, this is also exactly where the local or remote emergency manual trip push buttons are routed. To really put those speed constraints into perspective, if the turbine ever accidentally hits 110% of its rated speed, an electrical overspeed trip kicks in. This is the ultimate mechanical backstop. When 3,000 RPM is your standard running speed, pushing it past 3,300 RPM physically risks tearing that massive rotor completely apart, and nobody wants that. Section 5. Automatic and fired shutdowns. Controlled deceleration. Finally, let's look at the machine's ability to actually gracefully remove itself from service. This is what happens when a fault is definitely serious, but maybe not quite catastrophic enough to warrant a violent, instantaneous trip. Automatic shutdowns systematically, step by step, unload the machine to minimize any thermal stress. Think of it as a highly controlled retreat. It's triggered by issues like a rapid rate of change in compressor discharge pressure, often called CPD, or, say, if the inlet air filter differential pressure hits a high limit of 8 inches. When stuff like this happens, the control system calculates that it's just time to safely pack it in. Then we have fired shutdowns. These are a specific subset that handle fuel and purge anomalies. So we're talking issues like water injection backflow, super high fuel gas temperatures, or a false start drain valve that just refuses to close. The really brilliant part here is that the system intentionally keeps the flame lit just long enough to safely spin down the grid load. This protects the electrical grid from taking a sudden shock, while also saving the turbine components from rapid, damaging thermal contraction. It's pretty genius. Honestly, it takes a staggering amount of automated logic to keep the world's power grid running safely and smoothly. As our global energy demands just keep growing, and these machines are pushed right to their absolute limits, it leaves us with a huge question to ponder. How will these industrial immune systems evolve to stop the very assets that power our modern world from tearing themselves apart? Definitely something to think about. Thanks for tuning into this explainer, and I'll catch you next time.